Hello everyone and welcome to this second YMSC webinar. My name is Mohamed Elzeadani and I'm the chair of the second Young Members Subcommittee. And I'm delighted to have with us today Andri Setiawan, who will be given a presentation on fuse-based segmentation, the last line of defense against catastrophic building failures. Before I pass over to Andri, just a few points. If I may ask the audience to please keep your video cameras off and microphones on mute for the duration of the presentation. Also, there will be a Q&A session after the presentation, but in the meantime, feel free to type in any questions you might have in the chat. And also, please note that this session is being recorded and will be uploaded to our second YouTube channel. And therefore, by joining the call today, you consent that any views or information you share will be made public. And for our speaker today, so Dr. Andri Setiawan is a junior group leader at Universitat Politècnica de València, UPV. He leads the Andri project, which aims to develop a multi-layered defense framework to increase the structural resilience of critical facilities against multiple hazards. Andri also contributes to other projects at UPV, mainly Endure and INCAS projects, which are led by Professor Elzeadani. The Endure project aims to develop a novel fuse-based segmentation design approach to arrest the propagation of failures in building structures, whereas the INCAS project seeks to translate this new philosophy to specific applications to precast building systems. Before moving to Spain, Andri was a postdoctoral research fellow at EPFL Switzerland, funded by the Swiss Excellence Programme, and he obtained his PhD from Imperial College London. His PhD thesis was awarded the prestigious Adam Neville Prize for Best National PhD in the field of cement and concrete in the UK. So thank you very much, Andri, for agreeing to give the presentation, and I pass over to you.
Okay, thank you very much, Mohamed, for the kind introduction. So I will share my screen now. Okay, can you see it? Can you see it?
Yes,
okay.
Yes.
So yeah, good afternoon, everyone. So first of all, thank you very much for being here. And also for me, it's a really nice opportunity. And I would like to thank Mohamed and all the organizing committee of the Society for Earthquake and Civil Engineering Dynamics for organizing this webinar session. So today, I'm going to present you some key results on the projects that I'm working on in Universitat Politècnica de València. And as Mohamed has mentioned, the title of my presentation today is Fuse-Based Segmentation, the last line of defense against catastrophic building failures. So, okay. The outline of my presentation today will be divided into like 3 sections. In the first one, I'm going to give a bit of introduction about progressive collapse of structures, what are, let's say, the main definitions, and what is the, let's say, the consequence of having this kind of, let's say, phenomenon. And in the second part, I'm going to discuss in more detail about the design approach that we have in building guidelines for ensuring structural robustness. And then in the third one, I'm going to focus more on the main parts of the project that I'm working on, that is called fuse-based segmentation concept, from the perspective of the theoretical, let's say, background, but also the experimental validation. So let's start with the first part. I'm going to start with the sentence, our world is at risk, and let's see a bit some numbers that basically shows this fact. If you haven't read this report, I would encourage you to read. This is a very nice document. This is published annually by World Economic Forum. It's called Top Global Risk Report. And in the last one that is published very recently, they basically brought together collective intelligence of over than 900 global leaders across academia, business, government, international organization, and civil society. But also they, let's say, gain some information from 100 thematic experts, including risk specialists, and they ask, what are the top 10 risks that we are facing globally at the moment? So we can see here that in the top 2, We have state-based armed conflict, which is basically based on the geopolitical tensions that we have nowadays, but also extreme weather events caused by the climate change. And these two, let's say, top risks are a serious threats for our built environment. And let me show you some additional numbers. Here, I show you the data of the number of extreme events in the last 20 years from 2000 and 2019. And we can see that all these numbers increase significantly compared to the last 2 decades. So it shows that not only the hazards becoming more and more frequent, but also the intensity. And we can see that these consequences from these hazards are also increasing dramatically. In 2023 alone, a report suggested that this natural disaster have contributed to more than 70,000 deaths and causing economic loss more than 250 billion US dollar. So these natural disasters can basically create damage in our structural system, that if our structural system is not, let's say, resilient enough or is not robust enough, then it can create what is called like a progressive collapse. So we have seen this phenomenon in many different occasions. You can see here from the failure of several bridges, for example, the most recent one in Baltimore, but also buildings like in Eindhoven, New Orleans, but also, for example, in Miami, the Champlain Tower South in 2021 also. So let's start to define what is progressive collapse. There are many different definitions of progressive collapse from different, let's say, literature or resources, but I pick one from GSA. So progressive collapse is a situation where a local failure of a primary component leads to the collapse of adjoining members, which in turn leads to more collapse. And then at the end, the total damage becoming disproportionate compared to the original cause. So there are three keywords here. First one is local failure. So the local failure that we have in buildings or bridges can start either by vehicle impacts, or it can start because of like a small gas explosions or fires and so on. And what happens is this local failure then triggers further load redistribution in the system, and it can create further collapse. So you can see it as a domino effect or a chain reaction that leads from one position to other parts of the building. And at the end, the size of the collapse will be completely disproportionate when compared to the size of the initial collapse itself. I'm going to show you our group here in Valencia. We also work a lot of outreach. So we try to create this with this Mola kit, let's say, to simulate what is progressive collapse or what progressive collapse looks like. You can see here. So progressive collapse starts by local failure element. For example, in this case, we trigger failures of one of the columns in the buildings, and this triggers load redistribution, and then it pulls the rest of the buildings so that you have a total collapse that basically starts just by a local column failure in the third floor of this building. So now I'm going to move on to the second part of the talk. If we know that progressive collapse is dangerous phenomenon, it creates consequences, high consequences in terms of human loss and economic losses and so on. So what we do with this, how we approach this problem. So in this second part, I'm going to discuss about the current design approach that we have in our building codes or building guidelines to ensure structural robustness. So let's talk a bit about the philosophy. Please don't worry, this is the only slide, I promise you, in my presentation where I put an equation, because I think this equation is elegantly express the problem, right? So the total probability of collapse is basically a product of three components here. The annual mean rate of the occurrence of the hazard, the probability of having a local damage in one part of the building if hazard H occurs, and probability of having a disproportionate collapse given that the local damage occurs, right? So how do we minimize the total probability of collapse? Theoretically, you can reduce either of these three components, right? So of course, the first and most, let's say, logical one is to prevent the hazards to occur in the first place. So for example, this can be done by doing like let's say layouting of the building. No, for example, if you have some explosive or explosive materials in your building, some chemical materials, you need to store it. You need to store it in a location that is far away from like crowded place in your building. But it's in some occasion these hazards are unpredictable, right? So for example, if our buildings are subject to terrorist attack or bombing, you cannot predict this hazard in the first place. So what you need to do is to try to protect your key elements in your buildings, some strategic columns or walls in your buildings, so that they can withstand this threat without being, let's say, severely damaged, right? But if this local damage can still happen, because of course, once again, we don't know the magnitude of threats that we cannot predict, right? So the last attempt will be to try to, according to codes, of course, to try to provide our structures with sufficient ductility, sufficient redundancy, and energy absorption capacity, so that it can redistribute the loads from the failed components to its surroundings, so that you can, let's say, achieve a new state of equilibrium without propagating the collapse, right? So this philosophy that basically has been evolved for many years. The first code of practice in 1972 was published by ISTRAC-E actually after the collapse of Ronan Point in the UK. And then this code has been evolving a lot, adopted in the Eurocode, but also mostly in the US through the Department of Defense guidelines like GSA and UFC, and also the next generation of Eurocode. But according to all these codes, if you try to extract the key information, there are three key approaches to design buildings so that they are robust enough to prevent progressive collapse. First one is key elements. Basically, you need to identify what are the critical location in your building, and then you need to design these key elements so that they can resist a certain magnitude of pressure or forces, so that they can withstand even unforeseen threats, right? And then the other two, focusing more on the last part that I mentioned before, which is basically to create a system redistribution of loading by tying rules or alternative load path. With tying rules, what they usually do in practice is that you need to have like a continuous reinforcing system from one end to the other end of the building, so that you can tie all your structural elements together so they can act or work as a unit. Or alternative load path, which is basically a more explicit method where you perform a notional column removal in your building and then explicitly check whether your building has the ability to redistribute the loads from these elements to the surrounding part of the structures. So this afternoon, we are going to focus on this continuity or this tying rule. In what scenario, let's say, this continuity is beneficial and effective. And I also want to highlight in what other scenarios that this continuity can actually create worse situation, or it can backfire or create like a boomerang effect. So let's talk a bit about the duality of continuity. When continuity is effective, right? So I will play this very nice illustration video. It shows like three mountaineers in a mountain, and these three mountaineers are connected between one another using the safety rope, right? So why we need safety rope? Because if one of our group members slips and falls down, the other two can basically pull these falling mountaineers so that you can save these people, right? So this is the concept of continuity, and this has been proven effective in some real world incident, right? For example, here we have the New York building. This is basically next to the center. And this one also some buildings which were damaged by ballistic missiles in Kiev in Ukraine. So through this continuity, even with this sufficient damage, you can still maintain the integrity of your structure so that the collapse will not create further propagation. But let's see the other extreme. When continuity can actually backfire. Let's use the same analogy, but this time you are actually having a large group of people. Let's say you have a group of 15 people walking into the Mount Everest, and all of them are connected with the safety rope. But what happened is, in this situation, more than 10 person in your group falls down altogether. So what happened is that through the same safety rope, this 10 person can actually also pull the rest of the group down. So in this scenario, although of course this is the last effort that you will do, the only way to save the rest of the group is to cut the ties. Of course, you want to save it first, but if you cannot do it, what you can do is just to cut the.
And Andri, just to just stop you a bit. We lose your voice sometimes. I think the mic.
Okay. Now
it goes a bit low, but then comes back.
Okay.
Now it's very good, but sometimes it does it. I think.
Okay, I will try to. Now it's good.
Yes, it's good.
Okay. Yes. Thanks, Mohamed. Yeah. So in this situation, basically the continuity can have more negative effect rather than positive one, right? And the same phenomenon is actually has been used by if you perform like a building demolition of an old building using what is called implosion technique. So you can see here, this is a video showing an implosion technique. So what they did here is basically they put explosive in some key columns in the buildings, and then through the same continuity, they will pull all the rest of the buildings down. So you don't need to put explosive in all parts of your building, right? And we have done the same simulation in our group, and we see the same problem, right? So what I want to highlight here is if the same technique can be used by, let's say, building demolitioner to perform this implosion, it can also be exploited, for example, for malicious act, for like terrorist action, to perform the same procedure to destroy critical buildings. So let's try to see also a bit more some examples when continuity can actually create more catastrophic collapses. So for example, here, I show you 3 different examples. When you have a long, like slender buildings, one part of your buildings located in a soft soil, for example, and you can have local foundation settlements. So in this case, actually through this continuity, the part that goes down will pull the rest of the building. Or in the other case, where you have a wide span structures where the gravity dominates your system. For example, if you have a long span precast or long span post tension slab system, the failure of even individual column can actually create an overloading condition that pulls all the rest of the building down. For example, we did the simulation of a 10-meter span building. You can see here we remove one of the internal columns, and actually this propagates to the rest of the system. Or in the last scenario is if your column failure is not localized, but it involves a specific portion of the building. For example, this can happen if you have a large vehicle impact or sufficiently large bombing. So this can happen when the internal part of the building and then it spreads to the rest. So now I'm going to move on to the third part of my presentations about the fuse-based segmentation itself. So we already see some limitations on our, and in our projects, we try to find a better way to improve, let's say, our building performance so that they can also deal with the situation where continuity is less effective. So this is just an overview. Today I'm presenting 2 projects, Endure and NCAS, which is basically projects funded by the European Commissions. And the title of the project is Fuse-Based Segmentation Design, Avoiding Failure Propagation in Building Structures. And with a budget of around 2.5 million for Endure, and for NCAS is around 150,000 euros for the proof of concept, where we basically implement this fuse-based concept specifically to a precast building system. And these 2 projects are hosted by Universitat Politècnica de Valencia in Spain. It started in 2022 and it is scheduled to finish by the end of this year. So what is our source of inspiration when our, let's say, our group develops the idea? They say that nature is the best teacher. So actually what we see and what inspired us when developing this concept is the autotomy mechanism of a lizard, right? So lizard can basically deliberately shed or cut its tail to escape predators, right? And interestingly, we saw some very nice article written by Baban and colleague in Science, where they investigate the structural, let's say, the structural system, let's say, of the lizard tail, right? So in fact, this tail is not like a single monolithic unit, but it's more of like a socket or a ring that basically it can be detached by design. And the lizard only needs to move in some, let's say, movement to trigger this effect, to trigger this autotomy mechanism. So this tail is designed to break at a specific segment. And we want to take this inspiration and implement it to our building. So what we want to do is we want to combine the continuity when there is a normal condition, basically under surface load, under small initial failure, or when our building is subjected to, for example, surface wind loading and so on. Of course, we want to have continuity because the continuity helps to redistribute the loads so that we can have more robust and redundant system. But then, under extreme life-threatening conditions, we will trigger segmentation as our last line of defense to isolate the collapse. So the biggest challenge that we had in our project is to find a balance or find a harmony between the two. So we want to create a lizard-like buildings, right? That can redistribute loads, but also segment to isolate collapse. And our design space is basically in this part, in the overlap between connectivity and segmentation. If we have too much connectivity, it will propagate the collapse and pull all the rest of the building down. If you have too low connectivity, you are building a house of cards that basically tumble down very easily, even with small wind, small earthquake, and just an operational condition. So we need to find a balance and fine-tune a solution that fits in these two. So of course, when we develop a new idea, we want to test it. We want to do a pilot test to prove that the concept works. So we work on small scale first before we go further into a larger one, right? So we start with a subassembly level, which basically represents only a small part of a building. So here, we start by designing the fuse itself. Probably some of you are already familiar with the fuse in seismic, which is basically, we call it seismic fuse, to dissipate energy so that it can protect the rest of the structure from damages. But the fuse or the structural fuse that we want in our project is different with seismic fuse, because our goal is not to dissipate energy, but to actually localize damage and to control as, let's say, as a breaking point so that it will break there and isolate the collapse from the rest of the building. So there are no studies at all previously working on this specific goal, right? So what we did, we tried to first try to find some inspiration. We explore 26 different potential views for RC structures and another 22 for steel structures. As I mentioned before, most of them are coming from earthquake engineering field. But then we perform this multi-criteria analysis. We have 9 different criteria. Reliability, basically, I will just explain some of them. Reliability is basically, we need a fuse that is reliable enough, basically, to break at a specific load that we want with limited scatter, right? Because if the scatter is too high, then basically it doesn't work, because if the force is too high, then you collapse the whole building. If the force is too low, you create house of cards, no? So we want to have a fuse that is reliable and controllable in a way. Durability, of course, that doesn't really break easily, and it also be let's say, durable against environmental condition because it needs to survive the whole service life of the building. Compliance, whether it complies with another load path in your building, and constructability. We want to have a fuse system that is practical, cost efficient, and can be scaled to different buildings in the whole in every place in the world, right? So we evaluate this all different potential fuse design, and we end up that at the end, the best solution can be actually the most like the simplest solution, right? So what we chose at the end for especially for reinforced concrete structure here is mechanical rebar coupler. What mechanical rebar coupler traditionally do, they basically substitute splicing, right? So this mechanical coupler connect two bars in a location, and this mechanical coupler is designed to be stronger than the two bars that are connected to, right? So this mechanical coupler will force the fracture to happen in this bar or in this bar. So what we did, we reversed the way we think. We did the opposite. We have bars here, we have bars here, and we have the coupler here, and we want to focus or localize all the damage to happen in the coupler so that the coupler will act as a fuse. It will limit the force that can be transferred from one side to the other side. So we need to do some modification because the traditional coupler will not work on as our objective, right? So here, what we did, we tried to propose several different modifications by trying to reduce, let's say, the forces that you can transfer through this coupler. We have coupler that we create like a hole, basically, so you can reduce the cross-sectional area, or you create like a groove, basically you peel the skin of the coupler, or simply by making a shorter coupler. So you cut the coupler short so that the engagement length between the ribs and your bar will be less, so that the bars will slip. At the end, we perform all these very simple tensile tests with the universal testing machine. And we found out that our best solution is this short coupler. So basically, we can control the amount of forces that we want to transfer between these two bars just by adjusting the length. For example, here, you can see that having a coupler, shorter coupler basically limit the forces, the stress that you transfer in the bar to a very small value. And they also have a very easy to produce, easy to manufacture, and it's very accurate. It's very, let's say the scatter is very low. Okay, so now we have the solution for the fuse. The next one is how do we test it in a building system? So this is why I need to explain a bit the test setup that is typically used in progressive collapse. So in typical progressive collapse, the top two images there is the traditional test they use mostly in literature. So they are having 3 columns and then 2 edge column in the side, restrain, and then 1 column in the middle. You remove it and then you push the internal column to basically simulate column failure. You can do the same, but with slab. This is what is shown in the top right? But with this type of test, what you really evaluate is only the behavior of your beam. Basically, whether your beam can develop flexural, arching, and then eventually this catenary effect. But what happens is, with this type of setup, you don't really, let's say, simulate propagation of failure, because to simulate propagation of failure, you need to be able to capture the interaction between this beam and column, right? Because collapse propagation, yes, it starts from 1 column failures and then it propagates to the beam, but then this beam and slab needs to pull the columns and then create more successive column failures. And this type of setup is not able to simulate it. In the other extremes, we have either hybrid testing that basically combines computational model and lab, let's say, specimen, and then you transfer the degree of freedom from the simulation to your specimen. But this requires a special facilities, require a special methodology to perform, or a full-scale building system, which is very realistic, but at the same time, it is cost-intensive. So we don't have the tool even to evaluate how our fuse design can work in subassembly level. So what we did, we need to first develop our own new setup. So how do we do this? So first, we design a full-scale prototype building. So designing this building will help us to understand the system behavior that we want to simulate in our laboratory tests. And then we analyze various different collapse scenarios. And then we pick the most suitable scenarios that can basically be used to interpret or that can validate the effectiveness of this new fuse-based concept. So based on a selected failure scenario, now we have 3 different key parts of the building indicated by different colors. This red part, which is basically the part of the building that are assumed to be collapsed. So in this case, we assume a full collapse of the middle segment of the building. And then we have the yellow one, which is basically what we call as the segment border. Basically, it's the section where we want our fuse to be applied so that it can isolate the collapse from the collapsing base. And then we have the blue part, which is the remaining upright part that we want to protect from this collapse propagation. So based on this, I'm going to show you in the next slide. I think it's better here. Okay, we develop a new setup that can be done, let's say, without doing a full-scale building test, but it can also simulate failure propagation, unlike typical traditional progressive collapse setup. Here, we have the specimen. So the specimen consists of the ground floor column and then half of the first floor column. And we have the beam and slab around the segment border. Here, we applied a column pre-stressing system, which is basically representing the gravity load from the second and the third floor that we do not model in our specimen. And here, what is interesting, I don't know if you can see clearly, there are 2 hydraulic jacks there. One is vertical and one is diagonal. Why we need 2 jacks? Because when you have collapse propagation, the slab and beam system will have a transition behavior from flexural, and then at a certain level of deformation that is sufficiently high, you will trigger this catenary effect, right? So why we do need these 2 hydraulic systems together? Because we synchronize it so that at a certain level of displacement, in reality, you will have a certain magnitude of pulling forces. So we use this synchronized jack to have a kinematically consistent, let's say, condition between the internal force and the deformed shape of our system, right? So at the beginning, you just have flexural state. So you just basically push the slab and beam down. And then until a certain deflection limit, you start developing this catenary mechanism, and then you start synchronously pushing down and then pulling it from the strong wall. And the last part, we have this 2 steel frame at the other end of the building, where basically it represents the boundary condition, or it basically represents the lateral stiffness that constrain the segment border, and it represents the remaining upright part of the building that we did not simulate in the specimen also. So here we can basically simulate a system collapse propagation using just a certain portion of the building with let's say a specially developed loading protocol and boundary condition. So here is what I mentioned earlier. So what you did at the beginning, you just perform column pre-stressing to represent the gravity load from the floors above. And then at the flexural stage, you just basically push down the slab and beam until a certain level of deformation. And this loading protocol is extracted directly from the collapse simulation. So from the computational simulation, you can extract the deformation of the beam and the internal forces. So now we basically substitute these internal forces and deformation using external jack system. So in this case, in our case, which is scaled down specimen, after 100 millimeter is the point where you start having a transition from flexural to catenary stage. So now you have the 2 jacks are activated at the same time. So you push down while also pulling the jack. Phase 2. And finally, in phase 3, where you already have the slabs like inclined like a lot, you just basically only pull from the incline jack. So in this case, we expect that at some point in phase 3, we will trigger the fuse activation and segment the building before the column collapses, right? So our objective here is to protect the column in the border, because if the column in the border survives, you basically prevent the collapse propagation so that successive column failures behind these columns can be prevented. So this is the time-lapse video of the subassembly test that we performed. And you will see later that our fuse is located at a certain distance from the column, where you will see the segmentation plane or the fracture plane is going to form in this position. So what you can see there, I will pause it there. If you don't apply this fuse-based segmentation, what will happen is you will damage the beam column joint, because that's the position where you have the largest negative moment, but also the same pulling forces. But since we weaken this specific plane by introducing this short mechanical coupler, which is basically limited to a very low fault value, you force the system to break there before you completely damage or yield the column. So here we can basically limit the drift of the column before the pulling force go a bit more than that, right? So the fuse has been shown to be very effective in controlling the level of force that you allow different building parts to transfer between one and another. So we use the same system, the same concept, but for precast connection, we have performed 2 additional tests with different precast system. In this precast system, the fuse technology, let's say that we implemented, are a bit different, because it's easier with precast. They are not monolithic. So basically, you can simplify the problem by adjusting the connection to be weaker, for example, than the column, so that it breaks in the connection, but at a level of forces that not sufficiently to damage your column, right? So you can see here. So the drift of the column is very limited. I think it's less than 1%. So the connection breaks there. And also here, I don't know if you can see, this one doesn't have sound, but you will see there is a large deformation bump. Yeah. So it also breaks in the beam column interface after the corbel position. So we also create like a weakening plane in the position so that it breaks at a specific predefined location, just as the lizard basically cut their tail in a specific part of the body. Okay, and this is just to show you that we also employed photogrammetry system with this digital image correlation to capture the different damages that we have in the slab and in the column. Here you can see that the column cracks, but there are just limited cracks, let's say, and even the yielding, they are very low strain there. But the slab and the beam from the top, you can see that initially it starts cracking, of course, at the beam column joint, no, because it's the place where you have the negative moment. But then at failure, basically a new crack that is very wide starts to open in the location where you have the fuse. And this is basically the predefined fracture plane that we introduce in our system. Okay, so now we have successfully accomplished the subassembly test. But of course, as you all aware of, construction industry is very risk averse. They will say, okay, it works in subassembly, but we haven't seen anything in real building. So we need to prove it otherwise. So here, we also perform a complete building system level validation. In this case, we have this precast building. The floor area of this building is 12 meter, basically 6 meter, 6 meter. And then in the long direction, we have 5 meter base, 5 meter base. So 12 meter by 15 meter. and it has 2 stories with about 2.6 meter floor-to-floor height. So all the details that we implemented in this building system basically follow it basically follows all the requirements that practice adopts, right? So Eurocode, even UFC standard, we impose all the requirements in our buildings. But we tweak a modification. We made a certain modification in the connection that I will show you next. Here, to achieve the continuity, you need to take advantage of having this floor system made of hollow core to work together with the precast beam. Because floor slab is very effective in developing this flexural and also membrane action, right? So what we did, here actually we didn't do modification. We just follow a strict requirements of robustness guidelines in UFC, where basically you need to tie all your slabs and beams together. You put some ties between hollow core units like a U-bar, and also you have continuity bars in the top part of the beam, basically to provide some negative moment resistance between the one hollow core plank and the other one in the next bay. And we also put like a U-shaped ties that connects the hollow core beams with the perimeter beam. So you basically tie all your beams and slabs together so they can work as a unit. This is not new. This has been done in building codes. Now, what we do specifically, which is a bit counterintuitive, is this connection. If you refer to many different guidelines for precast system, for example, in FIB, they always recommend to use a full strength connection in buildings which are, let's say, let me redo it. FIB imposed the use of full strength connection to ensure structural robustness of precast system, right? Because with this full strength connection, you can develop the full plastic moment of the beam, and then you can basically connect the beams rigidly with the column. So you behave more like a cast in situ system. But what we do here is the opposite. We use partial strength connection, where basically you have these top continuity bars, but you also have these dowel bars that are also designed to rupture. So these dowel bars will rupture before all the top continuity bars yield, so that you can actually protect the column from excessive bending moment from the beam, right? Because here we need to think that our structural elements work in a system. In a system, there is interaction, and what we impose here is a hierarchy of failures. To achieve a structural system that can arrest collapse propagation, we need to protect the columns at all costs. So what happened here is the columns needs to be much stronger than the beams and the connections that are connected to this column. So here, the connections will be designed as a fuse system that basically segments in the connection or in the core bell position before the columns are being overloaded by this unbalanced moment and pulling forces. And this is the time lapse of the construction of the building specimen. So you start by erecting the columns, and then you place the beams on top, and then on top of the beams, we put the hollow core planks, we put all the reinforcement mesh, and then finally we cast the topping. So all of this process are basically a standard process that industry use. And now this is the testing condition. So I'm going to show you a video that explains the boundary conditions and how we load the buildings. So these buildings have 2 column hydraulic jacks. I will pause first. You see here, there are 2 edge columns that are basically made not of concrete, but of hydraulic jacks, because we want to remove these 2 edge columns at phase 1. And in this phase, we want to test the effectiveness of the continuity. So after removing these 2 columns, our hypothesis says that this building must survive by redistributing the loads from these 2 columns to the surrounding parts through the continuity that we have in the slabs and in the beams. Okay. And then Okay. Here we have a 3 steel hinge column. So this hinge column is basically the one that we will remove in the last stage in phase 2 to trigger the initiation of collapse. But our goal is to prevent this initial collapse so that it will not propagate to the rest of the building. So this 3 hinge column can be removed dynamically from outside of the building because it's like a 3 hinge, because it's like unstable column basically, right? So if you introduce a disturbance in the middle hinge, it will just like flip like this, and it creates like a dynamic situation, like dynamic column removal situation, and then it will trigger the collapse. But we will see later that it should stop before the collapse propagates to the rest of the building. Here you will also see all the sandbags that we put in the top, which is around 11.8 or 12 kilonewton per meter square, basically around 100, yeah, or around 12 kilonewton per meter square, which is very heavy. And you might ask, like, why we only put the sandbags partially in the building? Because this loading configuration is actually the worst scenario. You know, when this failure happens on one side of the buildings that we loaded here, we will pull all the rest of the buildings, and without having the loads on the part that are pulled is actually more critical, because with this load you have like a counterbalance, right? So you counterbalance this pulling force by gravity system that helps to stabilize. So we try to test this building with the extreme scenario where the remaining upright part was not loaded at all, so it will resist the largest unbalanced forces that can happen in a building. Okay. So next one, we put a lot of sensors. You can imagine we put more than 100 sensors here, strain gauges, accelerometers, LVDT, DIC system, and also other things, because we want to monitor everything. We want to monitor how the column load redistributed. We want to monitor how the beams can basically redistribute the load by developing these flexural mechanisms, and how the segmentation happens in the border that we design. So now let's see the video of the first phase of the test, which is basically to test the continuity. Here we can see that these 2 hydraulic jacks are being removed. Now one is already removed, and now we remove the other one. So I think this is also already an amazing spectacle, because it's not every day we see a building stand with the 2 columns are being removed from the place, right? And of course, you can see with your bare eyes or naked eyes that there's a huge deflection, yeah, in this position. I think it was around 6 to 7 centimeters, and the bars that are in these beams are already yielding, of course. But we can see that the structure is very stable. So in this phase, what happened is, okay, here I will just show you some numbers, but you can refer to the text for more details. Here, when we remove these 2 columns here, the load mostly goes to this C7 column, which is basically the internal column. And this can create already an overloading condition. So this is important to have a residual or a reserve capacity in your column, so that you can redistribute the loads safely to other parts of the building. What are the most interesting things here? There are one thing is the columns located far behind the building can actually experience like unloading. So the loads are being unloaded, because you imagine that this building now moves a bit like a seesaw. So one building is loaded more and the other building is a bit unloaded. In very extreme scenarios, as I will show you later, the corner buildings that are located on the opposite side of the collapse can actually go to tension. And this tension can actually create like a global overturning failure, because, you know, columns in buildings, they are mostly designed to resist compression. And these extreme scenarios, they can actually behave in tension. So this is also a lesson learned that we learned from this test. And here you can see the rotation of the beam is quite significant, and you have a yielding of this bar in this position. In the negative moment, you have the bars already yielded. And this one is the second phase, where now we test the ability of this building to segment. what we do here is we remove this corner column. So you can see here, the collapse was initiated, but it stopped just in the border where we plan to isolate it. So this is our segment border. You will see later from the top. Okay, this is the post-collapse inspection using drones. You can see here, this is the segment border that we created. So basically, all the connections break here in the corbel, in the dowel position. You can see the corbel are completely broken here, but the column survives without being overloaded. And here we also see some bone failure and slippage of the rebar mesh that actually helps in this scenario to achieve segmentation. Of course, bone failure usually is always anticipated not to happen, but in some extreme scenarios, this can actually be useful to allow it to slip. And here we have the rupture of continuity bars, but also the corbel is destroyed, but this corbel and the dowel bars here, let's say they serve their purpose as a fuse element. Okay, so now we also perform some computational simulation, and the simulation was done actually before the testing day. So we rely on the simulation to predict what happened in the testing day. And we were very happy because the prediction of our computational models were very accurate. Here you can see the comparison between the two. From different angles, and you can see how these buildings behave exactly it is expected in the real test. So another interesting thing is what happened if this building was not designed with the fuse-based segmentation, but instead if the building was designed according to traditional approach or according to current guidelines. So this is what happened. The one on the left here is the buildings that we designed and the one that we tested with the fuse-based segmentation. And the one on the right was building that is designed according to current standards. And with this full strength connection, what happened is this will actually pulse the columns and trigger the total collapse of the building instead of segmenting it as in our fuse-based design. Right? So, of course, because of the limited time, I cannot discuss further in detail, but if you are interested to know more, you can basically scan, if you want, the QR code here. It will direct you to the article where we report in detail the test results, the philosophy, and also some key data from the test. If you want to do some computational simulation, you can also use all the raw data that we put here. So our upcoming test campaign, I'm going to finish very soon. Our upcoming test campaign. So this is the steel building that we will test next month in March. And the steel building has the same size of the precast one, which is basically 12 meter, 15 meter in plan and 2-story height. And yes, we want to test the same thing here, whether this building can actually develop ALP in phase 1 and then can segment the buildings in phase 2. Here, what is interesting is we use the technology that is used in seismic design, which is basically reduced beam section in the beam. In seismic, you use reduced beam section basically to control the yielding of the beam, and then to protect the columns. But here we want to test it if it also works to isolate the collapse and then focus that the fracture happens in that position. So we will, according to our simulation, it works well. So fingers crossed that it also works well in our test next month. So okay, so fingers crossed for the success of the test for 2 reasons. Of course, the first reason is because if this test is successful, we prove that this method can be, let's say, scaled up to real buildings in construction, but also because our PI, our professor Jose Adam, he promised to share with us the harmony ibérico for the whole group if we manage to perform this test as good as the simulation. So fingers crossed for this. So to conclude my presentation, currently, our built environment is facing severe and more frequent threats from both natural, but also anthropogenic hazards. And this requires us, our society, to build more resilient infrastructures. And as I have demonstrated and explained before, that current design approaches to ensure structural robustness has been shown to work only for some scenarios, but can actually perform worse for some others. And this is basically the starting point of Endure and Encast. And the new approach that we studied here is called fuse-based segmentation, is currently being developed and tested to anticipate the limitation. And the core idea of this philosophy is combining continuity and segmentation in a single building system. The continuity is useful to prevent small initial failure so that we allow redistribution and to have sufficient redundancy and energy absorption in the building. But in unforeseen scenarios that are more extremes, that basically inevitable, the segmentation provides the last line of defense to arrest collapse propagation. So to conclude, as I mentioned at the beginning, our world is at risk, but we can create a more resilient society. So thank you very much for your attention. And I just want to acknowledge that all the presentations that I have today is the fruit of the hard work of all the members in our group. And also thank you for the European Research Council for funding this ambitious project. So thank you very much. I give the floor back to Mohamed.
Okay, brilliant, Andri. Thank you for a very interesting presentation. I think we can open to the audience for questions. So if anyone has a question for Andri, you could unmute yourself and also.
Yeah.
And in the
okay.
In the meantime, Andri, I was thinking, if say, so in the cases you showed, so failure was propagating at the edge of the building, and then you have the segmentation somewhere near the middle, which works perfectly. What if the failure propagates at the segmented part, and say you don't need segmentation, maybe you just need, to dissipate the energy by yielding of the structure as you did with the first two columns? Does the building segment at that point, or does it?
Yeah, that's a very good question. So basically, today I didn't have time to explain a bit the methodology, how we configure our buildings, right? Basically, we need to first divide our building as a Lego block, right? We have, I don't know, one segment and then another segment and another segment. And in this case, the size of the smallest segment in our building should be configured in a way to contain the smallest failures that propagates. So what happens is, if the failure is lower or the failure is less severe than what we designed the segments to break, it will basically just completely dissipate with us, as you said. Right? So if one segment only has like 1-2 column failure, that basically less severe than what we designed to trigger the segmentation, we will rely still on the continuity. So this segment will not be activated until an initial scenario that has the probability to propagate, so it will be just activated at the very last minute.
Okay, brilliant. Maher, I see a hand up.
Yeah, hi. Thank you very much for your very enjoyable and informative presentation. So my question is, do you have any studies showing how the fused segmentation system influences the collapse mechanism during a seismic event, and whether it affects the structural performance during an earthquake?
Yeah, that's a very, very, very good question also. The answer is we have, but now the work is under review. But I can share with you a bit. In this study, we basically compare two buildings. One without fuse, which is basically having all the elements continuous, and one building with a fuse system. And we subject these buildings with a simplified, let's say, protocol, which is like pushover analysis. So we perform pushover analysis in these two buildings. And at the moment, we expect the same behavior. And why? Because the position of the fuse, probably I didn't mention also earlier, is selected in a way so that it is not disturbing the development of plastic hinges near to the beam column joint. So in the concrete building, for example, we position the fuse actually closer to the zero bending moment line under surface condition, which is more than the typical length that you need to develop plastic hinge. So what happens is when you have this fuse, it will work independently to the plastic hinge. So the plastic hinge will be forming on its own. There is nothing, no disturbance at all. But that's a very key point.
Yeah, fair enough. Thank you very much. Yeah.
Thank you.
Dylan, I see a hand up as well.
Yeah, thank you. Again, thanks very much for a great presentation. I've never seen simulation results match reality as well as that has, so kudos to you.
Also.
Yeah, almost exactly. My question revolves around how do you see this applied? Do you see this being sort of rolled out on a building level, or do you see it being rolled out like you've shown in your presentation, where you have zones of protected zones sort of highlighted, and these fuses put to protect that zone, or do you think you could roll them out across an entire building, so that if a certain area was destroyed in a targeted event or whatever, would it work throughout the whole building?
Yeah, thank you for a very good question. Also, this one we actually have some recent studies that we published where we investigate the cost-benefit analysis of the fuse-based segmentation. Right. So the questions that we ask ourselves is, let's say if you have a building, how should we segment it in a way so that the cost of implementing this new technology is at least the benefit outweigh the potential risk that can happen if there is unforeseen extreme event, right? So yes, it can be applied in buildings everywhere in different locations, but you need to first configure your building into these segments, right? And the segments is determined by the risk that you anticipate, but also the largest collapse area that you can afford, right? So because let's say you divide your building into 9 blocks. What is the largest loss that you can have in the building that is segmented like this is 1 block of 9, basically, because the other 8 blocks will be behaving individually than this 9 block. So if you divide the same building into 20 blocks, the largest risk or the largest consequences that you can have is the failure of 1 block instead of 1 over 20 instead of 1 over 9. But of course, to have 20 blocks means that you need more segment borders. It means that you need to introduce more of this fuse system, right? So at the end, you need to find a balance between minimizing the consequences, but also the cost to implement the system. So now we are working on this. We have done a very preliminary study on a specific building typology, but in the future, we want to also expand it to other types of buildings. But this is how it works.
Mm-hmm. And do you find that there is quite a large economic difference between conventional construction versus this? Because I mean, I'm used to using couplers and things like that quite regularly, and if it was a matter of implementing adjusted couplers as fuses, that doesn't seem like too onerous a condition or too financially unviable, you know?
Yeah, exactly. So yes, we didn't see it as a burden or even like a big factor that can, let's say, hinder the application of this technology, but it's more about the planning of the building itself, no? Because this is a bit going outside of a typical traditional framework. So you need to include risk analysis, and also you need to plan in advance your building, how it segments and everything. But if you ask me about the cost of implementing the device itself, it will be very low cost. Mm-hmm. It will be very low cost, close to minimum.
So I see that being quite an easy argument. I work in UK nuclear, and we have parts of our buildings which are safety critical and certain parts that aren't. And so that sort of segmentation is almost outlined as part of our requirements. And so if we've got areas that need higher levels of protection, could be separated using this sort of mechanism? That's where I see its application. But no, thanks very much for the answers. That was great.
Yeah, thanks, Dylan. Yeah.
Okay. I don't know if we have any more questions, and we've already gone a bit over the allocated time. So thank you very much, Andri. I think we can end it here. Thank you very much for an interesting presentation. And yeah, hope to see you around. If you come to the UK, let me know.
Okay. Thank you very much, everyone, for attending. Thank you, Mohamed.
Yes, thank you, everyone, for attending, and see you in the next one, hopefully.
Yeah. good afternoon, and have a good day. Bye, everyone.
Thank you so much. Have a good day.
Thank you.